Okay, moving on to the last question of OST exercise 3, question 3. Okay, so it's a deductive question. Alright, so as per usual, we have labeled all the reactions numbered, so you can take some time to draw relevance to the numbers for the reactions that have been annotated. At this juncture, you want to pause the video to write down the numbers next to the reaction so that later on you can check against your answer. Okay, so we have compound M having a molecular formula of C13H16O. Alright, and then we have N decolorizing equals bromine. So this reaction, if you take a look at it, it can either be electrophilic addition, alright, which implies that it's going to be an alkene, or electrophilic substitution, where we have a phenol. Okay, so at this juncture we won't be able to know whether it's a phenol or an alkene, although the carbon to hydrogen ratio looks quite similar. So we keep it open, either electrophilic add or electrophilic sub. And then it produces white fumes with PCl5. Now, white fumes with PCl5, typically PCl5, we use it to test for alcohols and carboxylic acid. Alright, so the type of reaction that it undergoes is your nucleophilic substitution. Okay, so M will contain either alcohol or carboxylic acid. Now, moving on, we realize that it reacts with hot acidified KMnO4 to produce three fragments, N, P, and Q. So it's quite obvious that over here, this is going to be oxidation, and it must involve the alkene functional group. Why? Because only with alkene you have fragmentization of the molecule. So from 13 carbons, you can see it breaks up into 2 carbons, 3 carbons, and 8 carbons. Okay, so this will give you a clue that it's going to be alkene. So it's highly, unlikely that you have a phenol in an earlier component, given there's only one O. Okay, so now let's move on then. Okay, we move on to N first. Okay, N does not react with failing solution. So failing solutions, recall, what is it used to test for? Failing solution is to test for your aliphatic aldehyde. So there's no aliphatic aldehyde, and in this case, failing solution is oxidation reaction. Okay, next, aqueous alkaline iodine to form yellow PPT. Your yellow PPT will be your CHI3. Alright. And then you have your oxidation for your iodoform, which means that your N must have either CH3C double bond O or CH3CHOH. Okay? But if you were to take a closer look at this, if N is formed from hot acidified KMnO4, it is likely that this will not be possible, and therefore I should focus on N having this structure. Okay, and it's quite because of the iodoform reaction. Recall your iodoform reaction RCOCH3. As I mentioned earlier on, it's not going to be the alcohol because the alcohol will not survive the oxidation of KMnO4. It's likely a ketone. Alright, and then after the iodoform of the ketone, alright, what does it become? Alright, so if your I2 equals NaOH, heat, you get RCOO minus, and then of course your CHI3. So one look at this salt R is actually your RCOO minus. Okay? Can? Okay, so in this case, we can take a closer look at N and try to propose structure for N. To propose structure of N, N has very comparable C to H ratio, right? You can see, take a look. It's almost exactly 1:1. So it's likely to contain a benzene ring. Alright, so for N structure, it contains a benzene ring. Okay, and then you have 2 more carbons to play around with, and you must have the COCH3 in order to give you a positive aldophan test. So C double bond O CH3. So let's take a look at whether we fulfill all the components. We have 3 hydrogens and then remaining 1, 2, 3, 4, 5, 8 carbons and then 1 oxygen. So as a result, this N structure is a plausible structure. So let's draw out the N structure then. C double bond O CH3. So this is my structure of N. And with the structure of N, we can therefore predict what's the structure for R, because it's just simply drop the CH3 and becomes COO minus. So in this case, the structure of R COO minus, and then because of the Na, it will likely be N. Oops. It will be likely be Na plus. Okay, so I'm showing the thought process. Okay, so N and R, we have gotten a structure already. Now we move on to P and Q. Now P and Q both give, let me choose a color, let's choose green. Effervescence with solid sodium carbonate, effervescence with sodium carbonate. Now sodium carbonate is a classic test for carboxylate acid, right? RCOOH. Okay, and then in this case, orange precipitate with 2,4-DMPH, which means that on one hand P gives, but Q does not. So your 2,4-DMPH, it's your condensation reaction. It's a test for aldehydes and ketone. So in this case, P has aldehyde or ketone, whereas Q do not have. So in this case, let's take a look. Q has a very simple molecular formula, C2H4O2. So let's try out. Yes, carboxylic acid. So COOH. Okay, we are drawing the structure for Q. Let me use blue to draw structure. Q, COOH. We have 1 more carbon left. So 1 more carbon. I have used up 2 O's. I've used up 1 H. I'm left with 3 hydrogens. So this matches the formula C2H4O2, and therefore this is likely my structure of Q. So for such a question, my advice to you guys is actually to start off with reaction 8, because Q, alright, start with Q, and that means, in other words, you will focus your attention on 8 and 9, because Q only has 2 carbons. There's a lot less permutations in terms of the structure. Okay, then for P itself, for P, you have C3H2O5. You realize that this structure is this molecular formula is very unique because the number of hydrogens is very little. So the only way to have very little hydrogens, is to make my thinking visible. So I'm just thinking out loud. For P, I propose, because there's a lot of oxygens also, right? I propose to have 2 carboxylic acid group. Okay, 2 carboxylic acid group. So I've used up, because there's 5 oxygens, right? So if I use up a 2 carboxylic acid group, I have 1, 2, 3, 4 oxygens already. I'm left with 1 carbon. Alright, so let me join this up together. And then use up my 2 hydrogens already. So the only possible one is to have a C double bond O. And true enough, it's because of this C double bond O, it gives a positive 2,4-BTM-BH test. So this will be my structure of P. Okay, so structure of P, Q, N, and R are done. Now that we are done with P, Q, N, and R, alright, of course we will have to check our molecular formula again. P is C3H2O5. Alright, we've checked that. Alright, it's two carboxylic acid group. If versus the carbonate, the ketone here, C-O, can give an orange PPT with 2,4-DMPH because it undergoes condensation. Okay, now the structure of P, Q, R, and N, we now need to piece out N, P, and Q to get M. Okay, at this juncture, my suggestion is for you to pause this video, take a look at the structure. Okay, I'm going to review all the deductive statements first so that you can mark your work before I go through the structure of M. Okay, so in the next 1 minute or so, it will just be silence, showing you guys the deductive questions, the deductive statements. You guys can mark your deductive statements accordingly. So just take note, because 2,4-DMPH appear twice, sodium carbonate appear twice, the type of reactions and the functional group present, alright, I'll need accorded, alright, 1 take each. Alright, you don't get double credit for the same type of reactions and the same type of functional group reduction. Alright, so for 8 and 6, alright, they are the same type of reaction, same deduction. 7 and 9, same type of reaction. One is still condensation at 2,4-DMPH, just that one undergoes, the other one does not. Then you either have ketone aldehyde or no ketone aldehyde. Okay, then structure of Q and P, earlier I've gone through with you how I get the structure. Okay, and then we look at N. For N, reaction is of 4 and 5, so oxidation with filling solution does not. Alright, oxidation with alkaline equals iodine. So oxidation with alkaline equals iodine, so it contains either this or this. As I mentioned earlier on, we can conveniently strike out this because N is N is an oxidized product of KMnO4. So it's unlikely that your alcohol structures can survive the oxidation of KMnO4. So N does not undergo any oxidation in filling solution, so it does not contain any aliphatic aldehyde. So earlier I showed you guys how we deduce the structure of N. So N being a comparable C to H ratio as a benzene ring. So methyl ketone. Alright. Of course, you can also make use of the molecular formula to deduce that it's not possible to have the CH3CHOH group. And then, of course, the R, as we discussed earlier on, RCOCH3. Alright, when it gets reacted with iodoform, it will become RCO minus. So the CH3 becomes a CHI3. And that's how you get your structure of R. Okay, so we have gotten the structure of P, Q, N, and R so far. We're now going to focus our attention on the deductive statements for reaction 1, 2, and 3. Okay, 1, 2, and 3. So for 1, alright, in this case, it's unlikely to have a phenol because the O is, you can see it's not on the benzene ring itself, so it's electrophilic addition and contains your alkene. So in this case, since it has only 1 oxygen in M, and it reacts with PCl5, it is unlikely to be a carboxylic acid, but rather an alcohol. Okay? Because it's only a 1O. Alright? 1O carboxylic acid, you need 2 oxygens. So from this statement, M undergoes nucleophilic sub with PCl5. It only contains an alcohol. And last part with the reaction with KMnO4 in reaction 3. Alright? You have hot acidified KMnO4. So it's your oxidation with KMnO4 to give 3 organic products. Likely you have 2 alkenes present. So now that we have the structure of P, N, and Q, alright, we have 8 carbons in N, 3 carbons in P, 2 carbons in Q. We now need to join them up to get my M, which is the 2 alkenes. So suggestion, I can consider joining this double bond O with this double bond O, I can form a CC double bond. I can also join this double bond O here and this double bond O, alright, to form my CC double bond. So key idea, how to form CC double bond. The step involved, just quick recap. I remove this O, join. Remove this O, join. And of course, all the OH, I remove the O. Okay, then I join. So if I do stepwise approach, let me zoom out a bit so you guys can see in totality. Okay, let's take a look. I'm going to draw N first. So N. Okay, same orientation. Double bond, you can see a CC double bond. I join to now this part. Alright, this part. And then I have a H, so it is hidden over here. And then attached to one carbon. And then go down to this carbon now. This carbon will now be attached to this carbon here, right, through the two double bonds. And then I have a CH3 group. And then of course this is a H, so it's hidden. Okay, now we are left with this O, double bond O, and we earlier concluded that M has one alcohol group. So since we have a ketone here, this M likely must contain a secondary alcohol. And over here you can see a secondary alcohol will get oxidized to a ketone together with the breaking of the CC double bond to give back your respective fragments. So once you propose a structure, my suggestion is to check whether you can break up your alkene to form back your respective fragments. Okay, so I'll remove all the annotations now so that you can quickly take a screenshot of the answer. This is one possibility. In total, there are 3 possibilities. The approach will be very similar. Instead of now joining the double bond O's together in this particular manner, I can also consider other ways, right? Other permutations of joining the double bond O's together. So this is scenario 1. Alright, I've explained how I form the CC double bond. Now I'm proposing scenario number 2. Now I'm going to propose joining this C double bond O to this C double bond O here. Very similar as the scenario 1. So you can see it the same way. I'm joining up together and form a CC double bond. But instead of joining this C double bond O with this C double bond O, I can join this C double bond O with this C double bond O. Right? So now I'm changing Q with P. So let's take a look what happens if I change Q with P. So I'm now changing this. I form my CC double bond. Okay, so let's take a look at what's going to happen. So first thing first, start with N. C double bond O. Right, join to this. So this carbon here has a single H. So remember, I start to remove all the oxygens. Then I move on to this carbon with highlighted in pink here. So I move up. Notice the double bond is over here now. And now I have need to remove this oxygen, remove this oxygen, remove this oxygen. Right, so I have a CC double bond, alright, with a H hidden here and then a CH3 group. Okay, once done with this, then it's for this remaining thing. This remaining thing again, where I say M has an alcohol, but I have a carboxylic acid here. So this carboxylic acid must come from the alcohol in M. So what kind of alcohol gives you a carboxylic acid? Your primary alcohol. So you can see, okay, I propose a primary alcohol. Those of you who can't see that it's a primary alcohol, there's 2 hidden hydrogens here. So CH2OH is a primary alcohol. Again, when you propose structure, please check that the total number of carbons matches. So over here, 6 carbons in the ring, 7, 8, 9, 10, 11, 12, 13. Alright, see 13. 1O, the 6 hydrogens you can count on your own. Okay, so in this case, this is another possible scenario. I now, instead of joining this double bond O to the previous carboxylic acid, now join the ketone. Alright, for P and Q. This is scenario number 2. Okay, for scenario number 3, I'm not going to explain it. I'm just going to show you the answer, and then you guys can try to reason out how you can get a different answer, all right, from a different arrangement. Okay, so now instead of joining the Q to the C double bond O, the ketone of P, now I join the N's. All right, the C double bond O of N to the ketone functional group of P. All right. So in this process, what do I need to do to join them back up? I basically do the same as the earlier, remove the O's. And join them up. Okay, so benzene ring, CC double bond. Then continue with the pink color. So this is the orange. This is the pink. And then I have this carboxylic acid. Again, this carboxylic acid must come from the alcohol in M, and therefore I propose to have a primary alcohol here. Again, you can check the number of carbons. 6 carbons in the benzene ring. 7, 8, 9, 10, 11, 12, 13. Okay, again, when you check your answer, check the molecular formula, you check that when you break the double bonds, you can get back your N, P, and Q. The primary alcohol is oxidized to the carboxylic acid. Okay, with that, we are done with question 3 of OST 3. Alright, so in this case, I'll just scroll all the way back up to scenario number 1. Okay, let me just adjust it into frame. If you want, you can take a screenshot of this answer, the scenario number 1. Okay, so those of you who are finding it difficult, let me just color code for you to help you see where the double bonds are. Then of course the ketone and secondary alcohol. Okay, so you can take a screenshot of scenario number 1. Okay, scenario number 2, let me remove all the annotations now. Okay, I need to zoom out further a bit to capture everything on screen. Okay, so this one is this double bond. And then, of course, carboxylic acid comes from your primary alcohol. Okay, so you can take a screenshot of scenario number 2. Okay, moving on. Scenario number 3. Okay, same thing, I'm going to remove the annotation. It's the CC double bond over here. Now, and then of course for the carboxylic acid, it comes from this primary alcohol. Okay, so that's scenario number 3. Okay, thank you.